Can you see this okay? And actually, can I have one screen for the board? Okay. You can see this okay? Yeah, okay. So, so basically last time, right, we worked on generating random variables from normal, exponential, and the last one, if you got to it, was a gamma distribution. And so now what I want you, can I get a screen up? For random variables from each of those distributions. So let's see how this pen works. It's not too dark. All right, so we're going to sample we're going to take samples from each of these distributions. So these are three different problems, right? So you start with, say, the Gaussian distribution. You'll sample the Gaussian distribution. You'll calculate the sample mean as 1 over n, the sum of each of the random variables that you draw. Right, and we sort of talked about this last time. We didn't go into too much detail, but that the sample mean is also a random variable, right? So if I did this 1,000 times, I'd get the average of these random variables. That'd be some number. If I picked a new 1,000 random variables from this Gaussian distribution and took the average of those, I'd get a different number. Right, so the sample mean itself is a random variable. So I want you to think about calculating the sample mean with, I say, n of 1,000, and then repeat this process 100 times. Right, so I'll do this. Right, I'll do this once. I'll get a sample mean. I'll repeat. Where these are new random variables, right? So I draw another 1,000, a different 1,000 random variables. Keep doing this and do this for 100 times. And now we have this random variable that's a sample mean, and I want you to look at the histogram of that. Right? So hopefully, if our random number generator is working well, the sample means are going to be close to the mean of the true mean of the distribution we're sampling from. And I want you to think about what the spread of that looks like. Okay, so you'll do that for those three distributions. You should also calculate the sample variance. This formula I'm not going to remember off the top of my head. Not S. Yeah. Yeah. Yes. But it's a different 1,000. So draw 1,000, calculate this. Draw a new 1,000, calculate x2. Draw a new 1,000, calculate x3. Right? Because if you think about this, I mean, this is sort of basic idea behind any statistical sampling. If I were to ask you guys, if I was taking a survey and were to ask you guys a question, like say, how many siblings all of you have? Well, I would go and ask everyone, and then I could find the average number of siblings of everyone in the room. If I went and asked a different classroom of students, well, maybe I would get a number that was close, but it wouldn't be the same number, right? So we want to repeat this over and over again to get a sense of what the sample mean is. We do the same thing for the sample variance. And actually, if I have these, say I have a vector called X samples that has all of these samples in it, right? So it has this X1, X2, to Xn. I mean, you can go ahead and calculate the mean because this is a very easy operation. So you can do sum of Xsamp divided by n. But MATLAB, of course, I mean, it has a ton of built-in functions. You might have started to discover this if you're new to MATLAB. There's tons of built-in functions. So, of course, mean and variance are built in. So you could check yourself, right, and say, okay, I'll take the MATLAB function mean of Xsamp and the MATLAB function variance of Xsamp. And the variance is actually taking it's actually computing the sample variance. And I might be getting this formula wrong. There might be an extra n there. I'll have to look at it. But you can check it with MATLAB, and actually, if you do help variance, it will give you the formula they're using, so you can check if my formula is correct. Okay, any questions on the first part? Comments? Okay, so obviously, I mean, I think most people, well, clearly most people were drawing normal random variables. I think most people got exponential random variables working. The gamma distribution, remember, was the random variables. To sample from that, we use the rejection sampler. And I know at least a couple of you got that working, so maybe before we start this, we'll have you or someone else who got it working come up and show us how the rejection sampler works. Okay, so the second problem is to do Monte Carlo simulation to calculate this integral. Right, so I mean, we can all do this integral by hand, yeah? But remember, in the lecture we talked about breaking up the integrand in two different ways. Right, we thought about their function g would just be x cubed, and their distribution, actually 2x cubed, and then our distribution would be normal, so it would be flat. Right, the domain is 2, so the height of the uniform would have to be a half. So the first process is just to sample from uniform random variables, use our Monte Carlo integration formula, right? So let's see. We'll look at that if you don't remember the formulas. But so let's do it for a generic function. Right, so our function, which we're always going to decompose into the product of two functions, the integrand we're going to decompose into the product of two functions, is 1 over n, the sum from small n to capital N, of g of x sub n, where x sub n comes from f. Right, so the first thing we're going to do is draw f from uniform on 0, 2. And then our g in that case is 2x cubed. So we draw uniforms, we plug them into this function 2x cubed, and we calculate this average to get an estimate. We'll do the same thing where we looked at this quadratic distribution. Right, so we have this quadratic distribution here. That would give us a different g, because of course when I multiply the 2/3 x squared by the function g, I have to get x cubed back. And so now we're going to need to draw random variables. So for part B, we'll need random variables from 3/8 x squared, right? This is our distribution, where x is going from 0 to 2. Okay, so let's remember, because this is going to take an extra step of work, if I have some distribution here and I want to draw random variables from it, what do? What is the technique? So this goes back to the first lecture, right? So we have to integrate this to find the corresponding CDF and then invert it and then sample uniforms from that inversion to get the transformation. So we remember we need transformation. I think I'd also been calling it G, so let me come up with a new letter. We need a transformation let's say x equals, don't want F either. Let's say x equals h of y, where if we put uniform in here we would get back this distribution, or samples from that distribution. Yeah.
3 by 8 x squared. Get the x values from the norm.
Okay, so that's a really natural intuition, and it doesn't work. So the problem is, if you apply a nonlinear function to a random variable, you effectively change the distribution you sampled from. And in practice, if I just come up with some function, I don't know what distribution I changed it to. You have to think about it. Right? So to come up with the function, we need to integrate it to find the CDF. Right? The CDF is really what tells us what this transformation is. In general, it won't just be plugging uniforms in here. Yeah. But that's good. I mean, it's good you brought that up, because that is, it is sort of, it seems it should be that way in some sense, but it's not. Okay, and then also, for both of these cases, we went through the formula that would give you the number of samples we needed to get a certain tolerance with a certain probability. And we wrote down the formulas, and I told you what the answers were approximately. So I want you to go through pen and paper and verify the number of samples you need, right, to guarantee that I'll be, right, this thing's going to integrate to 4, that my Monte Carlo estimate, right, that sample mean will be between 0.39 and 0.41. I want to guarantee that happens 99% of the time. Right, and we went through the formulation that that we need to analyze to think about what n is, and effectively, right, it's finding the variance of this function g. Like that's what that's the work in it. Okay, any questions on that? Comments? All right. So the third problem is to do importance sampling. So again, basically we're just going through the examples we had in the lecture last time and actually doing them, right? Actually doing them. So we're going to use importance sampling to calculate the probability that a standard normal random variable is greater than 4.5. Right, and last time we saw that probability is going to end up being very small, too small to do Monte Carlo. So I mean, the first thing you could do is try, right? Draw 10,000 or 100,000 standard normals, right? Which is just the randn command in MATLAB, and see if you get any that are bigger than 4.5. Maybe you'll get one, right? But one isn't enough to provide you with a statistical estimate. Okay, so instead, right, what we saw is we were going to sample from a bias distribution or importance distribution, and the one we picked was an exponential moved over to 4.5. Right, we picked an exponential distribution, moved over to 4.5, and you could say, well, okay, I need to go through this integrate and invert process to sample from that. But really, we already know how to sample from exponential distributions with a given lambda. We did that problem. Right here we have a lambda of 1. And effectively, think of what you're doing. Right, if this is my exponential distribution with a lambda of 1, right, which look like this. If this was our exponential distribution with a lambda of 1, remember what we're getting. We're getting samples, more samples where there's more mass in this distribution, but samples all the way along the x-axis, although we'll get very, very, very few out here because this distribution function is really very small. Right? But effectively, what we're getting are x values. Right? And really what we want to do here, I should admit, I didn't go through this I didn't go through the integrate invert to prove to myself that it would work. So you might want to do that, then you would get the same thing. But effectively, all we're doing here is moving what 0 is. Right? So here we have zeros at 0. Really what we want is to move it over to 4.5. So I strongly suspect, I didn't check it, but I strongly suspect that effectively you could draw exponential random variables with lambda equals 1 and move them all over by 4.5 units. So you should probably go through and check with the integrate and invert from that CDF, remembering always, right, that this is just a number. So calculate that number first so you're not carrying around that ugly term. Right, that integral on the bottom is just a number. But then you'll get samples over here. Okay, so that's maybe the part that takes some thought. And then for importance sampling, remember instead of just plugging into the function g, which for our problem is 1 because we're looking for a probability. Right? We're looking for a probability, so our integral is the integral from 4.5 to infinity is this. I left off there's a 1 over 2 pi, root 2 pi. Right, so this is my distribution, and what I'm multiplying it by for this integrand is 1. Right, so we're really back to our first case, where we're only interested in counting the random variables that were bigger than 4.5. Right, but the difference between regular Monte Carlo and importance sampled Monte Carlo now is I have to correct my counting of these events that are happening with the likelihood ratio. Right, so really now what we're going to be doing is drawing our xn's from this importance distribution, which is just our exponential shifted over, 4.5. And I'm going to get a number when I do that, right? Maybe I get 4.9. I'm going to get a number when I sample that. Then I need to plug that number into the Gaussian distribution on the top, so 4.9 will go in there, and then into this exponential distribution on the bottom. Right, and that's the factor that we're adding up for each of these. For each of these samples and to do the Monte Carlo. Okay, any questions? I just said I took a sample from this exponential shifted over and it happened to be 4.9. Like maybe the next time I do it I get 4.52. Right? The real number, so the digits are actually going to go on further, but I'm going to be picking out numbers from here, but these capital XNs, they're going to be a number, right? It's a number you plug into both of those functions and take the ratio. It's not a variable anymore, right? When you do this process, it'll actually be a number that MATLAB gives you. Any other questions? So I think both this PDF and lecture 2 are posted. Is that true, Amit? Almost true? Okay, so it's almost true. So I'll leave this up for now. Oh, and maybe while that's being finished, we can talk about the rejection sampling. So does it, okay, so who wants to come up? I know. So do you guys want to come up since I know you have it working? Don't you have it working? Yeah.
One question.
Yes, of course.
Regarding the previous, you could calculate the ratio between the samples rejected and samples chosen.
Right.
When I tried it, I got it as 1.
You got a ratio of 1?
Yeah.
So you accepted all of your samples?
No, I mean, numbers, numbers actually came.
Right.
Right?
So you rejected all of your samples?
No, how if I'm supposed to get 1,000 samples which are true,
Uh-huh.
and 2,000 times. 1,000
Okay, so what the number you should get is dependent on the on the parameters you picked. So it should be whatever the area of the curve you use for the rejection sampling is. So it sounds like, if you're doing it correctly, that you had an area of about 2. Right, and then you'd expect to accept half of the samples.
So in general, we want to see to be high, right? We want more number less than 6.
Right.
We want our the new curve, if we ask close to commutative value.
Yes. Right, and this is sort of a theme, right? That the better we can do at estimating intervals and at sampling and sort of anything we want to do in this simulation framework. So you should find someone and have them explain it to you, right? And someone who's doing it for the first time, who really had to think it through, is going to be able to explain it better than I would be able to. Right, so that's going to be that's a homework problem, right? If you didn't get it yourself, have someone else explain it to you.
Let me try it again. Who does not have it working? So I think you ate enough, right? I mean, the food is not that bad. So who does not have it working? Sorry, please. I need to count, so I need to see the hands properly. 1, 2. Okay. Who has it working? 1 and 2. Okay.
Okay.
I guess we have to repeat the sample.
Yes. So come on up.
I have it on the web now. It's about 4 steps, right? Who has gone through first step? How many of you went through the first step?
So, and really, the very first step was done, right? You had to plot the 2 curves, right? And those curves were actually already commented out for you, so you could just uncomment them and plot them and start playing with the parameters, right? So even if this is very new to you, I know everyone can do that, right? That's
And the second thing I know everybody can do is integration.
yes,
Constant A,
yes.
for example. So who has done that integration? Constant A. In terms of the parameters. Okay, so there is a communication gap, right? I don't understand where you are stuck. And unless you tell me, I will not understand where you are stuck. So somebody please. Where is the problem? Right? Unless we see where the problem is, we can't help you. So shall we put do you have your first tutorial?
Yeah,
Is it here? I think it should be here. So I think the best thing maybe to put that.
I think it should be on this, yeah.
One, or step A. What's a choice? Somebody must have a choice, right? C0, A0, X0, 3 numbers you have to choose. What are numbers such that this condition is satisfied? Somebody? You must, I mean, you are supposed to choose 3 numbers in such a way that this function f of x is greater or equal this function qn of x for all x, well, positive, for all x. So what is one choice of such numbers? Two ways to do it. Either you do it analytically, or the second way is what's here in the second sentence. Pick some values, plot f of x, plot qn of x, and see what comes out. And for, how did you come up with these numbers? So, anybody else has any other choice? Okay, so did you get to this step at all in the first place, last time? No? No? Yes or no? I mean, there's 2 answers. Yes or no? No. I see 3 nodes. 4 nodes, okay. Any more nodes? I will assume everybody else got to this step. Okay, one more no. One more. Okay, fine. Finally, slowly they start appearing, surfacing. Right? Come on, if you don't get it, just say no, right? You can see that lots of people didn't get it. So if you think that I'm the only one who didn't get it, that's not true.
It's clearly not true. So
okay. So were you basically just focusing on problem 1 and 2 at that time, last time, or what was the? Where was the? Trying to understand MATLAB? Okay. So, but plotting the first, that you could do, or not quite? Or?
it's a tan inverse, and you want to factor out. Oh, it's already.
Square divided by a.
It's already factored the way you want to factor it, actually.
Yeah. So, but we want. I keep forgetting this. So I guess what's the best way to do this? Although in fact,
it's tan inverse.
It's just tan inverse.
Yeah, it's tan.
Either you know this integral or you look it up.
Right, and you know.
Or no, you can do it by substitution.
You can do it.
By substitution.
But you can also look it up. So I don't know. I don't know.
Right, okay, so x minus x0 divided by square.
That one's very light.
x0 over square root of a0 is equal to cosine of x. What will that give you? What's dx?
Can you see? Is this one?
Yeah, maybe that. Okay, so x, this term that's in the denominator, the square root is and what's dx? Okay, thank you. Minus sine theta times square root of a0. So if you substitute this and that in that integral, what do you get?
So you can substitute x minus x naught is equal to b. Because everything else is a constant.
It's just 1 over 150 squared. No, no, I don't.
Tan inverse, tan inverse.
So, oh, you happen to know it. Okay, I don't. I don't remember integration. So So if you substitute this, then what you get is, so there is C0, dx is minus sine theta, oh I guess I forgot the d theta square root of C0 divided by 1 plus cosine squared, which is sine squared. Theta.
No. 1 plus isn't.
Oh, it's 1 plus. Oh, so I guess I want here tangent.
You want tangent, yeah.
Okay, so I guess you have to choose a function which works.
So,
So anyway, but it's an integral that's doable, right? I think you can do this, you make mistakes, you can correct it, or you look up the article.
right.
You remember it.
And the only thing that's tricky, right, is being careful about the parameters.
Yeah, the constants.
Right? Otherwise, you look it up, and I don't know how it is in India, but in the States, the students are very sensitive. And I once wrote on a paper, so it's complex variables or some other course, that if you don't know how to do an integral, just look it up. And this was taken as an attack on the student. Or the student thought I was attacking them, that, oh, you don't know how to do an integral, oh, you're bad. Not at all, right? I don't know how to do integrals. I know they're in the back of the book, and I can look them up.
And you can see that I really wrote.
Yeah, right. Right. It's gone through this carefully, the form of the solution with the parameters in it.
C0, X0, and A. Okay, I think it will take what, 10 minutes?
Yeah, it may just go through and do it, actually.
5 or 10 minutes?
If you, is the new assignment online? Okay. So if you've already done this, the new today's tutorial will be put online, so you have something new to work on.
About that, but what was one of the, so to say, not requirements, but something desirable? You want a function which is somewhat close to this. Okay, so if you know a little bit of calculus, which all of you do, for sure, you just have to take it. Which is what basically Elaine was saying. This function, I'm going now to that screen. Sorry. This function here has a maximum at x equal to x0. Where was the maximum of qn? So it's coming back to this screen. Right? Coming back to this screen, you can see the maximum is say 3.5. I don't know, 4. So put 4. Take x0 to be 4 because you want the maximum to be around here. Okay, so that's one choice. Okay, so that way this whole thing will kind of shift. But you want to scale it down, right? What's this value? What's the value of the function at the maximum here? It happens to be 5. What was our choice of all these constants? A C0 was 5. So actually C0 gives you the value of the function at the maximum. What do you want it to be? You want it to be much less. You want it to be somewhat close to this value. So I don't know, is 0.2, 0.3, 0.5, something like that. Well, even 0.5 might be too much, less than 0.5. So say 0.3. Okay, so I get a choice of C0 and say 0.3.
And there's not a right answer for this, right? There are better answers and worse answers.
It's just a guess.
But there's not those are the parameters I should use for sure.
So what's the optimal choice?
The ratio of rejection should be equal to 1/1.
Okay, how will you optimize? So suppose I ask you to optimize the constant C0, X0, A0 for the best possible constant.
Take the area under the difference of the curves to be minimum as we know.
So you have the f function, which is this something like that. You have a q function which is that. You can write down the expression for the area between the two as integral. Right? It's what is that integral?
fx minus
F minus qn integrated from 0 to infinity. You can do that integral because
Because then it's 5.
n is 5. For n is 5 you can do that. Even for all n's.
For integer and
Oh, I mean for the integer. So you can do that. And then you can extrapolate it. So that will be the area between the curves. So that we call that area will be a function of a0, c0, x0. Minimize it. So that will be explicit expression for this, right? But there's a hitch. There's one big problem. You need to do this subject to the constraint that f of x is greater than qn of x and all points. That's a big constraint. So to put that in there, it's not easy.
And this is
So optimization problem under constraint are really hard.
it's
So you don't want to do
really
that.
hard, and then there's this other optimization problem that's your time, right? And how do you want to minimize the time you're spending on this problem? Is it doing an optimization problem like that? No, that does not minimize your time.
In this case, it would be better if you increase the size of the x-axis, because otherwise it will like
So you can take it to 20.
20 or something. So okay, I'm going to shift the maximum to somewhere around 4. Right? So I will take the x0 to be 4, c0 is 0.3. Well, let me just take it to be 0.5 just to be safe. And a0, I don't know what the integration for a0 is. Oh, a0 is a value at 0. Anyway, so something. I keep it, since I don't have an intuition for a0, I'll just keep it for details. I will reevaluate my f function, which is this. I've changed the constants, so I need to reevaluate this expression. Add that. So I do that. And once I do that, I can plot this new f function. That's where it showed up. Well, but it crossed. That was bad. X equal to 6. Maybe I made a bad choice.
A not. A not.
So I have to change it on. Maybe I will try not. So I guess should I increase or decrease it? I should increase. So A not sits in 1 over, but it sits in the numerator and in the denominator. So as x goes to infinity, what's the value of this function? As x is large, x becomes large.
C not. The size of the x.
I guarantee. So I can take x to be 10,000
Because
and maybe at 10,007 crosses.
the asymptotes of the size of the x.
1 lakh. I take 1 lakh. How do you guarantee that it does not cross at 2 lakhs?
But you can just move that over to 4.2.
So I could make this shorter.
Yeah.
But anyways, there's no point. Because the both point is the same point. Choosing the parameters is just a simple step. So now I will stick with. So I won't use these parameter values because they crossed. But I will use these parameter values which are highlighted now on the screen because they did not cross. And just stick with it. The curve is quite a bit above this curve, but also
step C, and then you come to this point, right?
So
then you come to D.
Part on step
basically.
C, right? That you need to infer that function.
Oh, I guess. Sorry. Yeah. Sorry. You need to write. Okay. This is G inverse. Yes. So you need
But
to.
it's really, it's already an inverse function. Like the easiest.
It's the easiest thing to invert because
Yeah.
there's a tan inverse, so you know that you're going to get.
Right, and everything else, besides the tan inverse and the x, everything else is a number. Right? I mean, this doesn't necessarily look like a number written this way, but it's a number. Those parameters are numbers. This is a function. Right? This is some number.
Yeah.
Choice of x not root a.
For this,
Yeah.
say, choice of square root of, yeah. So I guess I can do multiplied by C0 multiplied by and so on. But anyway, yeah.
Right. Doing the integration, doing the inverse. Right. That's much harder than the algorithm. The algorithm doesn't have any hard steps in it. Right. Once this is done, the algorithm is just drawing uniform random numbers and comparing them.
It's on now, okay. Everything else is really a bit simpler, right? Because we're drawing exponential or easy, right? We could do that no problem. Gaussian's easy, it's built in. And we didn't talk about how you would do that by, how it's done, but the algorithm is based on the same ideas. It's just a slightly more complicated case. So I think the work involved in the second tutorial is easier than the work for this one. So don't be, if you struggle with this, don't be afraid to try the problems in the second one.